Another confirmation of the quantum effects of electromagnetic radiation is found with the production of X-rays. The diagram to the right shows an X-ray tube, and there's an electric current that runs through this filament. And as the filament starts to heat up, it boils off electrons. And then these electrons are ejected and accelerated towards this metal target, and they're accelerated because there's a potential difference, a high voltage that is established between this filament and over here where this metal target is. So the electrons gain kinetic energy due to this potential difference that is established between here and here. The kinetic energy that it gains is equal to the electric potential energy. So you can think of K of the electrons is equal to Q times delta V. And since Q is a charge of an electron, we could replace that with E, and we'll just replace delta V with simply V. So the kinetic energy gained by the electrons is equal to the charge of an electron, E, times the high voltage that is established between here and here. Now, as the electrons come close towards this metal target, this tungsten nucleus, what we find is X-rays are produced, photons are produced, highly energetic photons. Now, where does the energy of these photons come from? Well, the energy of these photons come from the fact that when the electron is accelerated towards a nucleus, it suddenly slows down, and it loses all that kinetic energy it got from that potential difference. So the loss of kinetic energy is gained by the photon, and that is the photon energy is equal to that loss of kinetic energy. So anyway, the maximum frequency of because you can get a variety of different photons, but we're really only looking at the maximum frequency, and that's going to occur when all of the electron's kinetic energy is carried off by the single photon. So the energy of that single photon, you could say is E, is really equal to that change in kinetic energy, which is equal to E times V. Now remember that the energy of a photon is also equal to hc all over lambda, or h times f. Now we're looking for the maximum frequency, or correspondingly the minimum wavelength. So one could theoretically calculate the shortest wavelength of the X-rays that are produced. And that's exactly what we're doing in example number 3. So let's now turn down to look over here. This is the equation here. It's not written on your AP formula sheet. You have given this HF, and you're also given HC over lambda, and you're also given delta U is equal to Q times delta V. So you have to kind of link this up and say, well, the energy of the photon is equal to the kinetic energy that is lost by the electron, which is equal to the potential energy, which is E times V. So you can now write C over lambda equals E times V. And since we're looking for the minimum wavelength, and then we're going to be using this maximum voltage, or not the stopping voltage, but the voltage that is across the between the filament and the target. Okay, moving on to example 3. We have a potential difference of 87,000 volts. So that's our V. It's 87,000 volts. We also know that the charge of an electron is 1.6 times 10 to the power negative 19 coulombs. And we're asked to find, in this case, the minimum wavelength. So remember that we're looking for the shortest wavelength that corresponds to the highest frequency. The highest frequency is produced when all of the electron's energy is given up in the emission of a single photon. So the accelerating potential of 87,000 volts supplies the electrons with kinetic energy before they hit the target. And we do not need to know the numerical value really of E actually in this to find the kinetic energy. The electron's traveling through a 1 volt potential difference, it gains 1 electron volt. So you could take a look at this and say that the I guess we could say the E times delta V is really 87,000 electron volts. And that is the energy that is gained by the photon. So HE equals HF max, or HC all over lambda minimum. So therefore the minimum wavelength would be Planck's constant times the speed of light divided by the energy that came from the electron's kinetic energy. So let's substitute in here. I think the easiest value for Hc is to use 1.24 times 10 to the power 3 electron volts times nanometers, because I've already got this in electron volts here. And then we divide by the energy, which is 87,000 volts. You can see the electron volts will cancel out, and we'll get an answer of 0.0142, or 3, I guess, nanometers. But you could put this into picometers if you'd like, and it will be equal to 14.3 picometers. All right, that's it for X-ray production and an example with it too.